Hi, my name is Abby, and this summer I researched the mutualism between clownfishes and anemones. There are 28 species of clownfishes in the genus Amphiprion, and within those species there are 3 color patterns that have evolved independently and multiple times. First, we have our orange color pattern, which has evolved for clownfishes who specialize on the anemone R. magnifica. Our red color pattern has evolved for clownfishes who specialize on E. quadricolor. And lastly, our black and white generalist has evolved this color pattern due to their association with a variety of anemone hosts. Generally, it's believed that specialists are less resilient to disturbance than generalists. And however, we're seeing that our specialists are being found on host anemones that are not their preferred hosts, and we want to know if this changes their ecology. So the objective of this study is to determine if the ecology of clownfishes changes based on the anemone that they're using. We expect that our specialists will have the same ecology regardless of the anemone that they're on, whereas we expect our generalists to have phenotypic plasticity in their ecology, which is variability in their traits that they have. First off, we're looking at their overall integrative ecology. So I monitored videos of clownfishes on different anemones to see how close clownfishes stay to their host. We're seeing that our orange clownfish, or orange color pattern Percula, is staying close to both host anemones, whereas our red color pattern Melanopus is staying closer to their preferred anemone and further away from their unpreferred anemone. Lastly, our generalist Clarki is staying further away from both anemones. Next, I analyzed the video using Fiji and plotted their locations to answer the question, what is their territory size? When the fish are actually on the anemone, how much of it are they using? And so far, we're not seeing any trends in territory size across the fish. Next, I took a stable isotope analysis of carbon-13 and nitrogen-15 to assess the dietary niches of our clownfish. For our orange specialist, Percula, they have the similar dietary niche on both anemones, and they also have a similar dietary niche to our red specialist, Melanopus, when they're on their preferred anemone. However, when Melanopus is on their unpreferred anemone, their dietary niche is more similar to our generalists. So overall, we're seeing a pattern of these guys staying closer to their anemones and these guys being further away from their anemone, which explains why their diets are more pelagic and higher in trophic position. Lastly, we're looking at their anti-predator coloration. So when predators see the clownfishes on different anemones, do they look different? Our first graph shows us their luminance, or their brightness, and we're seeing that Clarki, our generalist, are brighter than our specialist and therefore easier to see. Next, we're seeing that our coloration, this trend suggests that our orange specialist is actually changing their color pattern on their unpreferred anemone. So Percula, they have these black bands and they will be thicker when they're on their unpreferred host S. gigantea, which is super cool. Overall, we're seeing that specialists have more phenotypic plasticity, more flexibility in their ecology than we expected, but in different ways. Our orange specialist Percula is staying close to both anemones, has a similar dietary niche, but they're changing their color. Our red specialist Melanopus is using the anemones differently, behaving differently on the anemones, which is driving the differences in their diets. And lastly, our generalist Clarki is further away from both anemones, has a more pelagic diet, and is brighter and therefore easier to see. We hope that the phenotypic plasticity in their ecology will allow them to have more resilience to disturbances in the future. Thank you.